Okay, hello and welcome everybody to the OSI SAF short course series. This is short course number 2 of 3, and today we're gonna hear about CIs and the OSI SAF CIs products. A few technical information at the beginning. If you have any kind of technical issues, if you cannot hear the speaker, if you cannot see the screen or anything like that, then please use the Zoom chat. And Regina, our technical support of today, will do her best and help you out. For questions on the content of the talks, please go to Slido and enter the event code #OCSAFICE. And please use this so that we can have a lively event today. All the material that we are sharing, the slides as well as the recordings, will be shared after the course on the course page, and the link you see here will also be shared in the chat with you. So this is our agenda for today. After the welcome and introduction, we're gonna hear about the different aspects of CIs and CIs characteristics, and we'll also see some application examples. And after each of the presentations, we'll have a look at the questions that have been posted to Slido, and we'll try and answer most of them. If we are not able to answer all of them, do not worry, we will keep all the questions and we'll answer them in written and also make them available on the course page after the course. A few words on EUMETSAT. Apologies if this is the second time you hear this, if you have joined on Tuesday already, where my colleague Haley has introduced this. EUMETSAT is an intergovernmental organization. At the moment, we have 30 member states, and our task is to take care of the European meteorological satellites primarily. So we develop them, we maintain them, and we operate them, and we make sure that the data are ready in time to be ingested into the numerical weather prediction models. That's one of our most important aims. But another task is also to contribute to the operational climate and environmental monitoring. And that's why we're also part of the European Commission's Copernicus program. We are not this is just an overview of satellites. We are currently operating in orbit and we are preparing for launch. I will not go into details for all of this. So if you're interested, then please refer to our webpage, eumetsat.int, or maybe also have a look at the recording from Tuesday. We are not exploiting the satellite data all on our own, but we are strongly collaborating with our member states with the so-called satellite application facilities. These are centers of excellence who are specialized in retrieving variables for certain application areas and user groups. And today we'll hear from the Ocean and Sea Ice satellite application facility. And there are many colleagues today who will introduce you to their work and hopefully attract you to their products. So today with me online are Steiner Eastwood, Fabrizio Baudo, Thomas Lavergne, Sini Aboy, Joanna Oelund, Jakub Hoyer, Joanna Caragalli, Stefan Hendricks, and Olivier Montbry. And your moderator today is Steiner Eastwood. And Steiner, with this, I hand over to you. The floor is yours.
Thank you, Christine. And let me just share my slides so I can give a short introduction to the OSI SAF. So hopefully you now can see my slides.
Yes, we can see.
Thank you. So the OSI SAF. So I'm the project manager for the OSI SAF CIS team, which we are colleagues from the Danish and Norwegian meteorological institutes that are a part of this OSI SAF CIS team. And as Christine said, OSI is a part of the satellite application facilities from EUMETSAT, and the Ocean and CIS SAF deliver key parameters of the ocean atmosphere interface. Among these are the CIS surface, no, the sea surface wind speed and direction, the sea surface temperature, and also CIS surface temperature. We deliver radiative fluxes, both downward, long wave and short wave. And today's subject is our CIS parameters. The OSI is it's a group of five cooperating institutes led by Météo France, and including the French research institute EUMETSAT, as well as the Norwegian, Danish, and Dutch meteorological institutes. So just to remind you, this is the second of 3 webinars. If you are interested in climate data records, that's the subject for next week on Tuesday, which also includes CIs, but then climate data records. So now an overview of our CIS products. CIS products is split in 2 groups in a way. We have the near real-time products, and we have climate data records. So today's subject is the near real-time products. These are the CIS concentration, the CIS edge, the CIS type, CIS emissivity, CIS drift, and CIS temperature. All these products are delivered both for the southern and northern hemisphere, so in that sense, global coverage. Just a few words then about what kind of satellite data we use. These are the satellites we use to retrieve these products. The SSMIS instrument, passive microwave instrument on the American DMSP satellites. We use the passive microwave imager EUMETSAT on the Japanese GCOMW satellites. From EUMETSAT, we use the METOP satellites with an optical instrument called AVHRR, as well as the active microwave instrument ASCAT. And then there's the American SUMI NPP and JPSS satellites, which carries the optical imager VIRS. And if we put some lines between the instruments and the products, you can here see which instrument uses which product uses which instrument. The CIS temperature product is based on the optical instruments of AVHRR and VIRS, while the other CIS products use active and passive microwave instruments. So if you're interested in getting these products, they are available on NetData format on our FTP server, as well on as our threads server. You can get them from EUMETSAT through the EUMETCAST transmission service or the EUMETSAT data center. They are also redistributed through the Copernicus marine and climate services. And for more information, please visit our dedicated OSI website, osisaf.met.eumetsat.int. So that was my last introductory slide, and I would now like to start the presentation of the different products by handing the word to Fabrizio and the CIS concentration.
Thank you, Stana. I'm just sharing my screen, and you should see my presentation, I hope. Can you see it?
Yes, thank you.
All right. So good afternoon, everyone. Thanks for joining this webinar. And in this presentation, I'm going to talk about the near real-time CIS concentration that we develop at DMI. So that's the overview of the talk. I'm going to give you some detail about the processing chain, then of course I'll talk about the level 2 and the level 3 CIS concentration product, and also give you some idea on how we do the validation to assess the quality and accuracy of the products. And then some future plan, because later this year we are planning to release an upgrade of the algorithm and the products. Very briefly, this is a flowchart which describes the process chain. Of course, I can't give you all the detail of all the steps involved, but I guess the most important part is the input data that we use for the processing for the algorithm. And we use data, microwave data observation from AMSR2 SSMIS according to the product that we generated. And in particular, our CIS algorithm, which is called the OSI hybrid algorithm, we use 3 channels of this microwave sensor. In here, I just put in lowercase that just for AMSR2, we have an additional secondary estimate of the CS concentration, which we call the TUD algorithm, which stands for Technical University of Denmark, which combine different channels with respect to the basic OSI hybrid algorithm. Another main source of input for the algorithm is numerical weather prediction data, and we use data from this NWFI resolution system. And we need this data because we need to calculate some radio transfer calculation. We need to do some radio transfer calculation to calculate atmospheric correction, which we apply to the observation, the brightness temperature, the observed brightness temperature. The process chain can be seen in a different way so I can show you maybe describing a little bit the timing and the generation of the products. So basically for one day, in 24 hours, starting from 00Z, 00Z to the next day, we receive a number of swap file. And as soon as a swap file is received by DMI, we trigger the beginning of our level 2 processing. And in here, you see this time, basically in our naming convention, this time, which is of course hour and minutes, is the time of the initial time of the scan of the satellite. So this is the convention that we use. And so basically when we generate the level 2 product, the naming convention, you will find this, the last 4 digits, which correspond to the initial time of the satellite swap. And the level 2 file product is an HCD file. It's an HCD file, and in this product, you will in this file, sorry, you will find the CIS concentration estimate for both the south and north hemisphere. And you will find a data gap between 40 south and 40 north. When we have received the process or the level 2 file, at some point here, the next day, generally between 2 and 3 in the morning, we trigger the processing to generate the level 3 CS concentration. In this case, the final product is divided for one NetCD file for the North Hemisphere and one file for the South Hemisphere. And the data convention, the naming convention in this case is just the date, which remember is the previous date with respect to when you actually the file is available here, and the flag with 1200Z, which identify the central window of the analysis time. Here it's a slide. This is the animation I started. It's a slide that I put just to give you an idea. If you never use the level 2 product, what can be the temporal spatial coverage? For example, if you're interested in monitoring application or data simulation application. So here there are all the swap file that we receive in 24 hours, so the corresponding level 2 product for the AMSR2. Instead, here underneath you have the sequential level 2 product, considering all the sensors that we use to generate the product. So the AMSR2 and the 3 SSMAS, F16, F17, F18. But this is again a sequential example of what you can get in terms of timing and observational coverage. This is another animation now, but for the level 3 product, and in particular, this is all the dates for December 2021, so last month. And what is relevant to see from this slide, I guess, is the difference in resolution between the level 3 product from AMSR2 and the level 3 product from SSMIS. Of course, AMSR2 has higher resolution and with respect to the SSMIS sensor, and so this is obviously is also impact on the final level 3 product. Just to say that obviously when we generate the level 3 product for the SSMIS, we combine all the swap file for the 3 sensor F16, F17, and F18. In this slide, I just try to put a summary of the products that probably, if you see this presentation afterwards, the webinar probably can be helpful for you. So in these 2 columns, I just highlight again what I was talking about before, the format, the resolution of the data, and the way the naming convention we use to identify the product. In here, you find something that already Steiner mentioned before, a link where you can find the data, and also other link where you can find quick looks at documentation. What I guess it's important to say, if you're a current user of the product, or maybe if you're not, in the netcd file, the main variable to look for to evaluate the CI's concentration is the string ice underscore concentration. Now, in the current operational product, this is a little bit confusing, but there is a discrepancy in terms of for answer to what we disseminate is what we call IceCon non-filtered. So non-filtered for us, it means that we just apply a CI's extent chromatology mask, while for the SSMIS, the ice concentration variable is what we call filtered. It means that we apply some screening tests, which are necessary to remove some possible false size over open ocean, and so to reduce the uncertainty of the algorithm over open ocean. Now, as I will tell you later on in the last slide, this discrepancy will be removed in the next upgrade of the algorithm. What about the validation? So the way we do the validation is, for now, we rely on US National Ice Center data ice charts. And we get this ice chart, we decoding the chart, we decode into the level 3 resolution. And then, of course, we compare with our product, and we calculate statistics like bias and standard deviations. And in these slides, we analyze the bias in terms of products minus ice chart, in terms of time series. And from this slide, I guess there are two main points to highlight. The first point is that, as you see here on the y-axis, the scale is the same. So the two products pretty much behave the same. And we have generally lower accuracy during summertime, better accuracy during winter time. But another main point to highlight is that the blue line is the statistic computing the current operational chain. As I said, most likely at some point this year we'll release a new upgraded version, and the red line show you the result from the new operational chain. And as you see, we are moving in the right direction, improving, reducing the bias in this case. The overall accuracy can be assessed looking at the standard deviation. And again, from this plot, this time series plot, we can highlight the same result as before. The two products behave pretty much the same. And again, the lowest accuracy is for the north southern hemisphere is always observed during summertime. And the best accuracy, of course, is observed during winter time. And again, the red line highlights that the new operational chain improve reduction in the standard deviation. The last two slides about a summary of what is going to be the release of the new algorithm. Probably for the user are not really relevant, but of course we have done a kind of technical scientific change to improve the chain, and most likely also to facilitate the use of new sensor in the future, like the answer tree and the microwave imager from the upcoming EPS second generation. But probably more relevant for the user, I highlight here, is that with this release, we also unify the documentation, so it will be probably easier for the user to look at the ATBD and the PUM, because we describe all the products in one single document. And this is even more important, I guess, because what I was mentioned before, in the current product, probably it's a little bit confusing in terms of the variable name that you find in the netcd file and the final product. What we have done now that we have unified the number and the name of the variable in both the level 2 and level 3 netcd file, final netcd file products. And we also make very similar to the CDR and ICDR CIAS concentration product. So probably the user, if you want to compare the near real-time product with the CDR, it's much easier than before. And the last slide, this is again to highlight what is going to be this change in terms of name of variable. Probably for the current user, there is not too much to worry about because, of course, the main variable, the ice corner will be the same. But as I said before, this will be the filtered CS concentration, whatever is the sensor, answer to SSMS. While in this variable here, the user is, if he wants to retrieve the so-called non-filtered value, the user can access to this variable to get what has been removed through the logic of the algorithm. And I guess this is it. I want to also thank, of course, all the OSI team at EMI. So thanks for your attention.
Thank you, Fabrizio, for this insight into the ice concentration product. Let's see if there's any questions now for Fabrizio from the Slido. Yes, so can you see the questions here, Fabrizio? The first
yes, I can see the yes.
So is the evaluation process for comparison to ground observations for CS concentration?
At the moment, no. Unfortunately, no. Probably we'll try to review also the way we do the current verification, but at the moment, no, we don't have any ground observation to compare with.
Yes, there are very few available ground observations. So what is the availability period of years for this data?
You know what? The near real-time data, I'm not sure how back in time goes, honestly. But if we check, I mean, if you can check on the FTP, you know, the main Norway website. Honestly,
yes,
I can't remember. Yeah.
The near real-time data production started in 2005, so we have a record of near real-time products back to 2005. But
Okay,
if you are interested in historical data, it's better to look at the climate data records.
About using active microwave, no, we don't have any plan to use active microwave, no, just passive microwave data.
Yes, so specifically for ice concentration, it's only passive microwave, while CIS Edge, for example, uses the active microwave instrument ASCAT.
Yes, about the next satellite mission, I briefly mentioned the last slide. Most likely will update when the EUMETSAT satellite will be available, but also the EPS second generation, the EUMETSAT satellite. So that's the plan for future mission. What time frame does the EUMETSAT concentration data cover? What I don't get, what does it mean time frame? I mean, as soon as we receive a swap file, in terms of timing of the swap file, a swap file is roughly 1 hour of observation. So if that's the meaning of this question, so you get one orbit of the satellite every 1 hour roughly, if this is the question is about.
Yes, and maybe it could be that they ask how long back does our EUMETSAT product goes?
Okay, probably. This we need double check on it. I can't recall now, but I guess EUMETSAT 2 has started at least 5-10 years ago, something like that.
And I think even longer, but also
maybe longer, yeah.
Yeah, the data, we also have a data record on soon for EUMETSAT 2 reprocessed, which will cover the full period of EUMETSAT 2.
Yeah, in terms of spatial temp resolution, so the level 2 files products are exactly matching the satellite resolution. So it means for each point of the swap file, you will find the estimate of the CIS concentration. Instead, for the level 3, it's just a regrading of all the level 2 products. And I mentioned this in the slide, probably I didn't say, but in the slide you can find that the final level 3 product is on a stereographic projection of 10 kilometers of breathing space. There's only one. I'm not sure what does it mean. There is only one satellite that can measure the temperature and several level other parameter. Maybe if you can reformulate the question, but
maybe
not really sure.
For the first slide I showed, there are several satellites that can measure temperature with infrared. There's several satellites. There's only one satellite for Arctic surface temperatures in microwave. That's the AMSA2 instrument. That's true.
Yeah, but we don't use, I mean, we use for the microwave, for the CIS concentration, we just use in the window channel. So the 19 gigahertz polarization, the 19 gigahertz, the 37 gigahertz vertical horizontal polarization. So we don't use really microwave temperature or humidity sounding channels. So we just using the window channels.
Yeah. Okay. I think that was the last question. We managed to get through them. If we didn't answer correctly what you were thinking about in your questions, please just raise another question and we'll get back to your question later. I think then okay, there's a new question there. Fabrizio, we have time for that. Are there any improvements considered in future methods, like exploiting more frequencies for handling known and underestimation of CS concentration for thin ice?
Yes, possibly looking improving also the use of higher frequency. So the other algorithm that we were mentioned that using the higher frequency, but of course it's more noisy, you can get more problem. But in the new release of the algorithm, we're using now a different radial transfer calculation method based on RT-top. So this might help to use also different frequency, because the more we have probably reliable radial transfer calculation to calculate the atmospheric correction, probably the better it is also for estimate the CIs. But of course, we need always dealing with window channels, because the window channel are those that are less sensitive to cloud contamination and scattering and so on.
Yes, thank you. And the last question is, I think we have also already answered that. Can you please explain if you use ground-based measurements in the validation? And we do not use that at the moment. There are very few ground-based measurements of ice concentration for global conditions. Then I think we can close the question and answer session for CS concentration, and we move over to a new product, the CIS drift products from the USAF, and Thomas.
Yes. Good afternoon, everyone. I'm going to share my screen. That you should now see full screen. All right, so I'm here today to present two CIS drift products we have at the OSI. We have the global low resolution CIS drift product, which has the tag name and identification OSI405, and I'm the principal investigator for this product. And we have an Arctic-wide medium resolution CIS drift product with an ID of OSI407, and my colleague Gorm Dubscher at DMI is the principal investigator. I'm going to present both products now in the next minutes. So first about CIS drift and how we measure it from space. Well, pushed by winds and ocean currents, sea ice is on the move. There are some regions where sea ice doesn't move, land-fast sea ice, but in the Arctic Ocean, in the southern hemisphere, sea ice is really on the move on a daily basis. And what you see here is an animation of daily brightness temperatures mapped from the Japanese EUMETSAT 2 instrument, one map a day, and you can see the motion of sea ice hopefully on your screen. So you both have the expansion of the ice cover because it's freezing at the beginning of the freezing season. But then once the Arctic Ocean is filled, you see that it's moving all the time because of winds and ocean currents. And the way we measure drift vectors is by analyzing day-to-day changes in sequences of satellite images. And so the job that your eye and your brain is now doing, tracking the motion, then we input that into our algorithms and let our computers do the work. Product information about this OSI 405, so the global product. As I said, the spatial coverage is global. We have a Northern Hemisphere and a Southern Hemisphere product file. The temporal coverage, we started this product in 2009, at the end of 2009 for the Northern Hemisphere. And then later came the Southern Hemisphere coverage since 2013. We use the continuous maximum cross-correlation algorithm, which is described in this scientific publication. We process both EUMETSAT2, SSMIS, and SCAT data. And the product resolution is at 62.5 kilometers. That's the grid spacing, so it's the spacing between the vectors in the product grid. However, the true resolution is probably more of the order of 100 kilometers. The drift period, the drift duration is 48 hours, about 2 days. But this is an average, and the actual start and end date and time of the drift vectors are for each vector in the product file. It's a year-round product, but we see reduced accuracy during the summer months. The product application is typically for general monitoring of the sea ice motion, validation and tuning of forecast models, data simulation, forward-backward trajectories, and probably not for analysis of climate trends. And we are preparing a sea ice drift climate data record that I will present next week. If you're interested, please join the seminar next week. But this near real-time product that I'm presenting today doesn't have the climate consistency to be used as a climate data record. Product evolutions, we are in preparation to run with the METOP SG satellites. So we will be using the MWI instrument, microwave imager, and the SCAR, the scatterometer instruments. And we are also planning to move to swath-to-swath drift products. So drift vectors from individual orbits of our instruments. A bit about the production steps. So at the start of the day, about 4 UTC, we build daily grid of satellite level 1B observations. We do that at 12.5 kilometer spacing for the whole Arctic and the whole Southern Hemisphere. Then we apply Laplacian filter to the image in order to sharpen the features in the image. Then we use our motion tracking method, the CMCC, at a 62.5 kilometer spacing. And we use the map we just created and the map we created 2 days ago. That's why it's a 48 hours drift vector product. Then we apply various filters because we want to detect and correct some rogue vectors that are pointing in the wrong direction. At step 5, we merge the single sensor ice drift products from EUMETSAT2, SSMIS, and SCAT into a multi-sensor product that we call multi-OI. We add uncertainties, production flags, and we prepare the final netCDF files. And finally, we distribute on our FTP and thread both the single sensor products and the multi-sensor product. And here to the right, you have an example map of sea ice drift for the Arctic, very recent, 2 days ago. And that's the single sensor SSMI SF18 product. And you see that there are different colors for the vectors, and that's because of the different quality and production flags. So when you use our products, please take a look at the production flags. You see, for example, that close to Greenland, and here at the opening, there is a lot of dynamic, and SSMIS was not very good that day to catch the dynamic. But then EUMETSAT2 was doing a better job in this region. EUMETSAT is generally doing a better job of CS drift than SSMIS. And so we also have this product. And then finally, we do the merging and we propose this, this daily product that has information from 3 satellite sensors and also interpolated vectors as violet here. On the product performance, so first concerning coverage, OC405 achieves complete daily coverage of the Arctic and Antarctic sea ice every day. But you have to expect larger interpolated regions during summer. For the accuracy, we do validation against ground-based data with the GPS drifters, and that yields RMSEs of about 2 to 7 kilometers on each component of the drift vector. The RMSEs depends on the instrument. So EUMETSAT is better than SSMIS, that is better than ASCAP. On the region, the Arctic is generally better than the Antarctic, and the season, the winter, is better than the summer. To the left, you have an example validation plot over 6 months at the end of 2019. EUMETSAT in the fall season of the Arctic. So you see RMSEs of 2 kilometers. On the right, you have an example of the multi-sensor product validation in spring, southern hemisphere. And here, the standard deviation is more of 6 kilometers. So you really see a change of the accuracy. Also, what we do is we try and track buoys or objects over a longer time period. So here you have a tracking of from the 1st of January to the 1st of May of the track of the mosaic in red, and the track, a simulated track from the ice-drift product in blue. And you see that in that case, it's working very well. Application examples to the left is where we use the OC405 product to simulate 10 years of drift trajectories for the mosaic, starting from January 2020 here. And we could show that in the 10 earlier years, the polar stern would have drifted much slower. And to the right, it's an example from very recent. Actually, the last frame of this animation is today's product, where you see that there is a lot of dynamic around the Svalbard and the Greenland region, and it's due to a low pressure passing in that region. And so you can link the melt freeze here and the advection. So that was about OC405. Now I'm moving to the other product. I will go a bit more rapidly on that one. It's OC407. So it's only for the Northern Hemisphere. It started in April 2014, and we use here a maximum cross correlation. Here, the main difference is that we are using thermal infrared data and visible data from AVHR. The product resolution is about 20 kilometers, and the drift duration, the drift period, is 24 hours. We require clear sky, and that means that there are quite some gaps in the coverage, and the precision requirement is 2 kilometers per 24 hours. So product application, climatological studies of the drift characteristic, but again, the time period is currently a bit short, and ice model validation and tuning. In the future, OC407, it's running on AVHR data from METOP B, so we will move it to METOP C, and it's being prepared for EPS-SG satellites. So that's the production step to the left. So here we process individual sources. So we first grid individual sources on the Northern Hemisphere grid. Then we match it. We match it with a maximum cross correlation routine, and then we apply a 5-step filter routine to remove erroneous vectors. And then finally, uncertainty estimates are applied, and we ship the product to you. And so to the right is an example. At the top, the raw maximum cross correlation output. So that's not something we distribute. That's really our internal product. and then the filtered output that you receive at the bottom. And you see that there are much less vectors than in the, or much less coverage than the OC405 product that I presented earlier, but also you have a higher resolution. We do validation against buoy data, and so the OC407 performance for 1 month of data is shown below. So that there is very little bias and very high precision. And here the standard deviation of the error is less than 1 kilometer, so it's 800 meters. So that was covering the 2 CIS drift products of the OSISAF. Again, OC405 global low resolution, OC407 Arctic medium resolution. And I hope you learned something. And if you have questions, I'm happy to answer them. Thank you.
Thank you, Thomas. Good to know more about the 2 different ice drift products. There's already a few questions for you. Maybe we should start here. Yes. Do you look at year-to-year patterns in CIS drift? Are there regular seasonal patterns?
Yes. So at the OSISAF, we have 2 hats, right? We are producing the data, and then we want to analyze it ourselves. So as I said, for the OC405 product, it's rather short, right? The production started in 2009, and it cannot really be used as a climate data record. But still, we are looking at, we and others are looking at climatologies and deviation from the climatology anomalies in drift speed and direction over the last 10 years. And we can see we can see the general pattern, but we can also see when there are anomalies.
Thank you. And then about the timing and here, is there a reason why you use the maps from 2 days instead of the previous days, 2 days ago? So,
yep, that's is there a reason? That there must be one. It was a choice that was made when we started the development. What we see now is that we could do also a 24-hour drift product, especially with IMSR2, because there the RMSE, the accuracy of the vectors is sufficient so that we do 24-hour drift product. However, we are going to wait for that. We are going to wait that we move to swath-to-swath drift. And then we will be really doing the matching of individual swathes, for example, at 12 hours apart, 24 hours apart, and that will really bring up.
So I think we are losing you a bit, Thomas. But
oh, sorry.
Yeah, essentially it was a choice made to for reasons of accuracy, but you're prepared to do better temporal resolution when you go to data, yeah, swath-to-swath based processing.
Exactly.
Then there is a question about ice concentration. Maybe if you see if there's any more on. There's a couple of more questions here on ice drift. Yeah, can you please explain a bit the term drift? You use it in different contexts: drift period, CIS drift, or drift products.
Yes. So it's something we say. CI scientists we say CIS drifts, meaning that it moves, meaning CIS motion. So here I used all drift always in the sense of CIS motion. So for example, when I say drift period, it's the duration of the drift vector, or it's the duration of the motion vector.
Good. We have time for one more question.
Yeah.
The rest of the questions will be asked answered in the Slido, but
okay. So
let's
there are
check the question, Thomas.
Yeah, so there is the one, does the algorithm perform any separate fast ice identification? No, not at this resolution. And are there plans for a high resolution product? At least not much high resolution. We will add the temporal resolution. Okay, you have to stop me when the time is off, but for sensitive, yeah.
I think we stopped there, Thomas. I think actually the last one is quite interesting with the model data. Is daily average data of sea ice motion of model data okay to compare with sea ice drift, or should we take longer averages?
So there is a simulation currently ongoing. So the Copernicus Marine Service assimilates the OSI sea ice drift vectors, and they do the averaging of the model data to 2 days, 48 hours before they compare. And I think you really should do that. So you have to average to the 2 days, otherwise you don't get the same signal.
Thank you, Thomas. And maybe then Thomas can have a look at the Slido and give answers to the rest of the questions there, while we give the floor now to Signe Åbo, who will talk about sea ice edge and type.
Yeah, hi, this is Signe from Norway. Can you hear me?
Yes, thank you, Signe.
Perfect. I will just start sharing the right screen. So hopefully you see my presentation now.
Yes, that's good.
So yes, I'm Signe from Norway, and I will present to you our two products on sea ice classification. The one is sea ice edge, and the other one is sea ice type. So in the first presentation, we heard about our sea ice concentration product, which presents the areal fraction of the surface covered with sea ice. The sea ice edge is a similar product. However, instead of giving the fraction of sea ice in each pixel, it divides the surface into different classes. In this case, in the figure in the middle, the classes are closed ice, which is ice typically more than 70% concentration. We have the open ice class, normally a small band along the ice edge. And then we have the open water class. The concentration product and the edge product show to some extent the same thing, but they are based on completely different algorithms, and they have also different input data. Finally, we have the ice type, is another classification product, and this one divides the sea ice into the older multi-year ice and the younger first-year ice. And then we have an ambiguous ice class, which can be either pure multi-year ice, first-year ice, or a mixture of these two. In this product, we define multi-year ice as all the ice that has survived at least one summer melt, but this can be differently defined for other products, so you should be aware of that. In other words, this ice type product is an ice age product with only two IH classes. You should note that these classification products, they have defined the open water class as ice-free, or everything that is less than 30% ice concentration. This also differs from other products or from typical ice extent index. So be aware of that if you're comparing with ice products. In the following, I will focus mainly on the ice type product, since the ice edge product is similar to the concentration product. So how do we measure from space if the ice is either multi-year ice or first-year ice? Here I have the animation made by Thomas that he showed in the previous presentation, and it shows the brightness temperatures at 36 gigahertz from the passive microwave radiometer answer 2. This is one of the channels we use in the classification algorithm. And this animation is running during the winter of 2019 to 2020. For comparison, I included a small map below showing the minimum ice condition in the previous summer of 2019. So at the ice minimum in summer, all the remaining ice becomes multi-year ice. And during this first summer melt, the largest changes in the physical properties happens. So these differences in physical properties, which can be measured from the satellites, they're possible to detect. So you will see the multi-year ice here as the more purple colors, darker purple colors, and the first year ice in yellow-orange. So as you can see here in this animation, the multi-year ice is relatively stationary north of Greenland and north of Canada. And this is both during the winter and also from winter to winter. And the main motion we see is the export through the France Strait, which causes this decrease of multi-year ice during the winter. So this relatively stationary distribution of the ice type, we use this in the algorithm for training the algorithm computation. So we use data from regions with known ice types. Here in the figure, we have multi-year ice in the region of the green circle, and we have other places marked with red circles where we never expect to find multi-year ice. This method of having daily updated training data has advantages such as being able to capture the seasonal variability and the interannual variability. Is also a good way to facilitate inclusion of new sensors. Of course, there's also disadvantages of having these fixed regions, since a region may not represent the same class for every places. So for example, the training data from the multi-year ice region, it originates from the oldest part of the ice pack, and it may not always present the younger part of the multi-year ice in other places. Also, we see that these daily updated training data, they appear to cause a lot of daily variability, such as noise. So something we have to look into. So a very short summary of the technical specification of the ice type. So per now, it's a global product. For this table, I will focus on the northern part of the product. This has been operational since 2005. But note, as said in the previous presentations, even though we have an archive of data back to 2005, these data are not climate consistent and should not be used for climate studies. The method is and has always been the Bayesian statistical approach, where we now use the daily updated training data, and we have some post-processing filters. It's a multi-sensor product where the input data today is the AMSA2 and the ASCAT scalerometer. And then we also use the passive microwave SSMIS as a backup for the AMSA2. The product is provided on a 10-kilometer grid, but the true spatial resolution is more about 20 kilometers. The temporal resolution is daily, but only during winter months we are able to classify the ice type. In summer periods, there will be problems with melting at the surface, and we cannot make a good classification yet. In addition to the main variable of the ice type, we also provide the status flag telling about the processing and an uncertainty field. Since last year, we finally introduced an ice type product for the Southern Hemisphere. It's based on the same method as for the Northern Hemisphere, however, with some adjustments. So we use now fixed training data, and we have included an ice drift masking. I will come back to this on the next slide. For now, this product is only a single sensor product using AMSA2, but we are planning to include a scalerometer in the next version. Otherwise, the technical specifications are the same on the grid resolution and temporal resolution and the available variables. Since this Southern Hemisphere ice type product is newly released, I will just use another slide on this. Here you see an animation showing the ice type product during the first year of its release, where the multi-rise is shown in black. We see at the beginning of the animation that most ice melts away during summertime in the Southern Hemisphere, but some ice do remain, and this is mainly in the Weddell Sea and in the western seas of the Antarctic. This is where we expect to find multi-rise. You will see that while the new sea ice starts to form, we also see that this multi-rise is more dynamic than in the Northern Hemisphere. Especially in the Weddell Sea, you will see that there's an offshore drift. So since most of the ice melts away during summer and the remaining ice is pushed toward lower latitudes, which is also warmer, the multi-rise in the Southern Hemisphere will not get as old as in the Northern Hemisphere. So these differences require some adjustment for the algorithm to better fit the Southern Hemisphere. So I stopped the animation and I included now the three fields, both the ice type variable, the status flag, an example of this, and an example of the uncertainty for the same day. So yes, I already mentioned that we, instead of using daily updated training data, we use a fixed data set from 2016, and it's a single sensor product. But most importantly, we have included this ice drift masking, which is very crucial for the Southern Hemisphere classification. So all this post-processing and activated filters we're using, they are locked in the status flag, and they are also adjusted in the uncertainty field. Short slide on the validation. Both for the ice edge and the ice type, we use ice charts from the ice services. Typically, we will use the standard ice charts of concentration and compare the edge in the high resolution charts with our products. But we also use the stage of development charts to do visual inspection to our ice type products. On the more operational quality assessment of ice types, since we are lacking observations, we do a monitoring of the temporal variation of the extent of multi-rise. This is based on the assumption that we will not expect too large or too rapid changes. And also we will expect a decreasing extent during the wintertime, at least in the Northern Hemisphere, because in the Southern Hemisphere, we actually find an increasing extent during the winter months. And we expect that this is due to some divergent drifts. So here's an example for the last year. In the Southern Hemisphere, we see the multi-year ice extent is increasing. And my final slide is on future plans. And we have a long list, but firstly, we will make preparation to run with upcoming satellites. As already been mentioned, we have the ESP second generation satellites with a new passive microwave radiometer and the new scalerometer SCAR. We will also focus on the Southern Hemisphere ice type to make it into a multi-sensor product to include scalerometer. And then we have a list of known issues that we are planning to make a better handling on these. So for instance, we have the ice drift masking, which is very good for the Southern Hemisphere. We have ideas to improve this one, and we will implement that to the Northern Hemisphere as well. We also have problems with multi-rise disappearing when we have a temperature anomaly, a known issue, which we refer to as warm air intrusions, when warm air is going over the ice. And we will implement correction schemes for handling this. And then we have other things on our list, like reducing the summer period where we don't have classification, and reduce the daily variability, and so on. So this was the end of my slides. Thank you.
Thank you, Signe, for an insight in the ice edge and ice type. We have time for a couple of questions here. Yes, the first one is the Ice Age product available for the Antarctic, or the ice type product?
Yes, the ice type, which is also an ice coarse resolution Ice Age product, is available in the Southern Hemisphere, as I showed, but since last year.
Can multi-year ice be used to monitor climate trends and more generally the different sea ice types?
Yes, I would say that is a very good indicator, because we see that multi-rise is decreasing in extent, and multi-rise is also the parts where we have thicker ice. So this is for sure a climate indicator. We have not done that in the OSI, but you're welcome to use the product to make your own climate indicators.
And then another climate-related question here. Are you planning to process all the data for the Antarctic ice type when you get the algorithm tuned, or will there be only newer data?
In this OSI products, which are near real time, the main goal is to improve it to be the best possible algorithm with the available data today. But we're also working in another project, the Copernicus Climate Change Services. And here we are making climate data records out of the ice type. We have not included Southern Hemisphere yet, but this is also something we will be looking into in the future.
Good. And then finally, does the Ice Edge product also include the detection of leads and polynyas?
Only in the sense of if the polynya is less than 30% ice concentration, it will detect that it will be an open water class. But of course, if we have a low concentration of ice, we will still detect it as a polynya or open water, which might not be true if you are looking at the concentration data in addition.
And then we have more time for one final question here. How about the threshold? Ice-free, less than 30% has been selected, and what is the threshold for full cover ice?
Yeah, good question. The threshold of 30% is a historical threshold, and it's been chosen at a point where we did the validation against the ice charts, and this compared well with the threshold in the ice charts. And it's also, since the lower concentrations are more difficult to capture correctly, there are more noise over open water, and this is something the ice concentration product has worked a lot with. So for now, we stay with the 30% to concentrate on the ice cover, not on the thinner ice or the lower concentration ice. But this could be something to change in future versions. The threshold for the full cover, the closed ice in the ice edge, is all the ice with more than 70% ice concentration.
Thank you, Signe. And just a quick answer to the last question about your training data. You said they were daily training data.
Yeah, this is a good question, and I didn't make this clear enough. It's daily updated training data set, but the data set itself consists of 15 days. Yes, so we all the time collect data for the recent 15 days, but this data set is updated on a daily basis.
Thank you, Signe, for those clarifications. We will make sure that all questions are answered in the Slido afterwards. But now we need to progress to the next presenter. Johanne will present the sea ice emissivity product.
Yes, I will just share my screen. So, and hopefully you can see it now.
Yes, thank you.
I'm Joanne, and I'm from DMI, and I will present the sea ice emissivity product. So the intention with the OSI sea ice emissivity model is to provide an early estimation of sea ice surface emissivity for atmospheric sounding. The model can be used as a proxy to detect ice and no ice regions and characterize the physical properties of sea ice and surface. It also provides information about first-year ice and multi-year ice and the seasonal variation. Although sea ice microwave emissivity is well defined in terms of brightness temperature and the effective temperature, it is difficult to derive it in practice. Here I have some of the technical specifications. The satellite input comes from SMMIS, and the model uses AMSU data for validation. It uses a level 3 observation, and it provides daily grid of the model coefficients, and the spatial sample is 10 kilometers. The estimated emissivity is provided for both sea ice and seashells in the Arctic and around Antarctica. The model uses brightness temperatures measured at window frequencies 18 and 36 gigahertz, where the sensitivity to the atmosphere is minimized. And here I've made a flowchart describing the process of the model. We have the OSI sea ice emissivity model, which is based on the correlation between the brightness temperature at 18 and 36 gigahertz. It uses the brightness temperature to compute spectral gradient ratio and the polarization ratio, and from this we can compute the model parameters R and S, which are used simulating data from a combined thermodynamic and emissivity model. And from this we can then compute the sea ice emissivity product. The spectral gradient ratio and the polarization ratio are used to predict the emissivity for horizontal and vertical polarization at incident angle between 0 and 60 degrees. The first figure shows how the sea ice emissivity at 50 gigahertz is related to the gradient ratio for 18 and 36. The second figure shows how the polarization ratio for 36 and 50 are related together with the neighboring frequencies of 18 and 89 gigahertz. The polarization ratio is used to verify if and how the simulated data of 18, 36, and 89 compares to the measured data of 50 gigahertz respect to the polarization. If we use the linear relationship in the two previous figures based on the simulated data, it is possible to estimate the 50 gigahertz emissivity at a 50-degree incidence at vertical and horizontal polarizations in terms of gradient ratio and the polarization ratio, and the parameters S and R, as we can see in the figure. The 50 gigahertz nadir emissivity of first-year ice in the Arctic lies from 0.9 to around 1, and that's the yellow and dark red we can see in the figure. And then we have the multi-year ice emissivity from around 0.7 to 0.8. And between that, from 0.8 to 0.9, we have a combination. The emissivity product is validated in two different ways. We have the simulated surface emissivity from the OSI model together with the HEALAM surface temperature. And this is used to simulate brightness temperature and then compare it to an AMSU sounding observation. And the figure shows that the AMSU channel 4 brightness temperature, but we can also use the channels 3 to 6 for validation. The OSI model shows a good fit with the observed brightness temperature. The other way to validate is using various emissivity models with the earlier methods. And here we show the result for a time point model and a dynamical method. There's a good correspondence between the different emissivity estimates, but the dynamical method has relatively large scatter. Compared to the emissivity from literature, the OSI model compares closer than the other models, especially regarding to multi-year ice. For the future, we are preparing for the new MWI sensor, which is planned to launch in 2025. This sensor has other channels, but does not include the frequencies of 36 gigahertz that we use now. And this means that we need to develop a new method for computing the emissivity using the new provided frequencies. And this is already well on the way. And that was all I had.
Thank you, Johanna, and your team at DMI for presenting the emissivity product. There is one question already for you on Slido. Do you address the effect of dry/wet snow in this product?
I don't really know how to answer that right now, but I will look into it.
Yeah, we'll get back to you on that. How this emissivity model deals with the surface specifications. And as far as I can see, that's the only questions on.
There is one more now.
Oh, there. Very interesting. Is there plans to also estimate uncertainty of this in this emissivity product?
Yes, but I haven't gotten to that yet.
Yeah, so there's plans, and as all OSAF products, there will be also an uncertainty estimate in the future upgrades of the product. How do your observation compare with emissivity models? Are they using such models as input?
Well, they are compared to emissivity models.
Yes, that's what you showed in the validation, right?
Yeah.
How about the use of your emissivity?
We also use emissivity models in the beginning of to find in the beginning of the model. Let me just see where we have to find the parameters.
Okay, yeah. And a new one here. How do you think this emissivity product will affect or change the CI's temperature product shown last webinar?
I don't really know how to answer that as well.
No, it's I mean, this emissivity is there is also in the emissivity product is there some ice temperature parameter is there, yeah. Which comes along with the ice emissivity product. Yeah, we'll get back to that that question as well. Maybe we can also hear from the next speaker on this issue with the ice surface temperature. Yeah, I think that was the last question. So we say thank you to Johanna and move along to Jakob, who will speak about sea ice surface temperature product.
Yes, I will. Good afternoon, everybody. I'll just share my screen. Let's see. All good. Great. Yes. So I will present some of the.
Jakob,
Yeah.
do you have presentation mode maybe?
Yes, I have. Doesn't appear like that.
No, it's not yet. It's in normal PowerPoint tool mode.
Oh, that's strange. Just a second. I'll try sharing again. Is this better?
That's much better. Thank you.
Okay. So I'll kick off again. Just saying welcome, and I'll present some of the characteristics and some information on the OSI high latitude sea and ice surface temperatures. Let's see. Okay. And the outline of the talk and the topics I'll mention in this talk is, first I'll briefly define some of the characteristics of the ice surface temperatures and motivations for why such a product is useful. Then I'll talk about the algorithms that we are using to retrieve the surface temperatures, a bit about the product specifications, timeliness, resolution, and so on, and the performance when we compare against the in situ observations. And then in the end, I'll briefly mention something about applications and some planned developments in the future. So first, the ice surface temperature. Well, I should say that I'll mostly talk about the characteristics and the nature of the ice surface temperature in this talk, even though it's a combined sea surface temperature and ice surface temperature product. But I think Stefan in the webinar on Tuesday covered the sort of the nature and the characteristics of the SST product very, very well. So I'll focus mainly on the ice surface temperature here. So what is it that we actually observe or we get in the product? We derive the infrared. It's infrared clear sky observations, and it's the skin temperature of the snow and ice surfaces. And why is that important to emphasize that? Well, it is really that it's the top layer of what we see of either the bare ice or the snow on top of the ice. And that's important because you can see in the figure, in the lower figure here, you can see some of the observations that we do from observations at weather stations in Greenland. We can see that it's the blue line is what is represented as the infrared observations, similar to what we see from the satellite. Whereas the cyan curve here, the warm cyan curve represents what's observed from a temperature sensor under only 8 centimeters of snow. So that means that if we have a snow cover on top of the sea ice, the temperature signal is really uncorrelated to a large degree to what we observe on the top of the snow, on the very skin of the snow on top of the sea ice. So it's important to emphasize that the product here is the skin of the snow or the skin of the bare ice. Also, what's important from this figure, and what's also characteristic for the snow and for the observations in the product, is that we see large temperature variations over the sea ice or the land ice. We see the large diurnal temperature variations on the order of 10 degrees. So it's not unusual to see these temperature changes within a few hours, maybe a day, on the order of more than 10 degrees. And that's, of course, also to be compared with the sea surface temperature, where we see much smaller diurnal variability. Let's see. Then I'll just see. Yeah, so why is it important with the high latitude SST and ice surface temperature to have such a product? Well, first of all, it's because we have a very poor coverage of good and reliable and representative in situ observations in high latitudes. We do have some observations of temperature from buoys drifting around on the sea ice, but as you can see in the figure here, if they get covered by snow, and they very often do, lying around there for extended periods, then it's not really representative of the surface temperature, and also not really representing the 2-meter air temperature, the near surface temperatures. So that's very important to have the wide coverage, the uniform coverage of the satellite observations. And what you can also see actually on the panel here is also that we have model temperatures. The 2-meter model temperatures can differ significantly due to the lack of observations in the Arctic, and where you can see we have a monthly mean difference of more than 8 degrees in, let's say, in the month of September. Oops, just a second. So the algorithm that we use to provide these products, or to process and deliver the product, really consists of 3 algorithms, where we first have an ice surface temperature algorithm, and that's a split window algorithm used or derived on the basis of the findings in Key et al. In 1997. It's updated, of course, but it uses the same principles, where we have currently calibrated in ice surface temperature retrievals calibrated for 3 temperature intervals. In addition to that, we have over the ocean, we have the sea surface temperature algorithm, where we have a separate day, night, and twilight retrievals. And then lastly, we have the marginal ice zone algorithm, which we define as the zone where we have both surface temperature, both open ocean and sea ice, and where we have a combination of both SST and ice surface temperature algorithms. So it's important to emphasize here that the coefficients are calculated through a regression analysis, where we use a simulated radiator transfer model to derive the top of atmosphere brightness temperatures. A bit about the specifications of the product. First of all, we call it a global product, but it's really it's northward and it's polewards of 50 degrees north and south. It's covered here, and it's the products have been running in near real-time since 2016. We have single sensor products, both level 2 and level 3, where the level 2 product is this OSI 205, and where we have one product from the METOP B AVHRR in a 1 kilometer resolution. It's northern hemisphere and southern hemisphere. And then we have also a 205B, which is based on the MPP VIRS in a 750 meter resolution, only for the northern hemisphere. In addition to that, we have aggregated level 3 products that are consistent with the level 2 products, where we aggregate the data in 12 hourly products on a polar stereographic grid with a 5 kilometer resolution. Input to the retrieval comes from where we use the Polar Processing Software Cloud Mask, PPS. We use the OSI sea ice concentration, and then we use temperature and wind parameters from NWP. Output is, of course, the surface temperature. It's over the ice, land and sea ice. It's a sea surface temperature, and it's the marginal ice zone surface temperature. And along with all the retrievals, we have uncertainties, quality level, and probability of clouds. In addition to that, we have in the files, we have the information about sea ice concentration, NWP, derived temperature, and winds. This is just a slide on the performance. We do a routine validation, similar for SST as what we learned on Tuesday, that we compare against drifting buoys. As you can see from the table up here, daytime, nighttime, bias and standard deviations. And then the lower table here shows the ice surface temperature validation, where we compare against this sheet is a comparison against Greenland ice sheet observations, where we have a PROMICE atmospheric weather stations set out around the Greenland perimeter. And in general, we should say it's very limited. As I said, the in situ observations, good reference observations from sea ice are very limited in terms of numbers. So the most stable and reliable validation results we get is actually from the Greenland ice sheet, even though we still have a larger sampling error in terms of the in situ observation not representing as directly as for the SST, not representing the skin of the surface. Yeah, and I should also remember to say we also have some challenges. It's important to know when interpreting or using the observations that in general it's challenging for the cloud screening over sea ice. I mean, a cold and white surface can look very much similar to a cold and white cloud. So we do have some, there is a tendency for some challenging and some contamination over the sea ice or the ice in general, in particular in nighttime. And this is, of course, something that we are working on improving. This is just an example of applications where you see high resolution. These products can be used for high resolution monitoring, near real time of the sea ice surface temperature, as it is here for a fjord in northwestern Greenland. And they can also be used for applications where they feed into, for instance, the CMEM's Arctic product. And I think Joanna will demonstrate that later, how these data are taken up to produce a level 4 product that covers all surfaces of the ocean and sea ice in the Arctic, and is really useful for monitoring the sort of daily climate and the daily environment, the daily surface temperature for the full Arctic, and compare it to climatic conditions. In the next development phase of the OSI SAF, we will look upon including a few new products. One of the products is the ASTI version 3. And I should say ASTI is an acronym that's where we have a version 2 and a version 1, and it stands for the Arctic and Antarctic surface temperature. And it's a climate data record where we have produced in collaboration with METNO, DMI and METNO have produced a version 1 and version 2 outside of the OSI SAF. But in the next OSI SAF phase, we'll include the ASTI as a version 3. So that will be a new product. And then, of course, we'll also have the implementation of the MEDimage and the NOAA 21 BS ice surface and sea surface temperature products. And the running improvements in the next phase and the future will focus upon the cloud and ice and sea classifications. We will focus upon improving quality algorithm and also on the associated uncertainty values that comes with the product. And yeah, I should remember to acknowledge the whole DMI team here, but especially Gorm Dybke, he is the main guy working on these ice temperature products. He couldn't be here today, so I have taken over, but if there are any questions I can't answer, I'm sure that Gorm can provide you with a good answer today. Thank you.
Yes, thank you, Jakob, for that insight into the ice surface temperature part of our combined SST-IST product. There is already one question here about ice buoys.
Yes.
Can ice buoys not have the temperature sensor on a motorized stage that keeps it above the snow level?
That's a good question. Well, in general, I should say that we are actually we have just started a project together with EUMETSAT on trying to develop a new type of cheap, reliable reference in situ observations that can be used for these type of validations. In general, motorized things in very cold conditions and in the Arctic, I think that's I haven't seen that, but yeah, it sounds challenging. But we are I should say we are looking at the moment on maybe deploying some thermistor chains sticking from the ice and sticking out of the snow into the air. From those, if the density is large enough of the thermistors on that chain, we hope to be able to derive the surface to be distinguish what is the surface and where is the air on a sort of routine basis.
So good, there is progress, but as Jakob said, it's partly also the fact that these observations are made in very hostile and conditions where there's you're not able to come back and check the instrument because it's in the inner ice. Then, do you have any data about the sea ice albedo? So,
well, that's also a good question, and we have some experiments, and we have performed a few experiments in the fjord off Greenland, on the northwestern Greenland, to work with the sea ice albedo. But it is one of the uncertainties in the retrievals, I would say, to determine the albedo, and it's not incorporated on a routine operational basis in the algorithm, if that's the question.
Yeah, so there is no sea ice albedo product or data from USAF, but I would advise the person in question here to also search other sources for that kind of data. What is the accuracy of a sea ice surface temperature if it's on the edge of seawater? Yeah, so close to the ice edge, what's the accuracy?
Oh, of the product. Yeah, well, that's also a good question, because again, I mean, I was mostly talking about the lack of in situ data over sea ice. In the marginal ice zone, the lack of data is even worse. We do have, however, some comparisons using the ice bridge flight campaigns, where we compare this data against our satellite retrievals, and it seems like in general the retrieval is doing a fairly good job with a similar performance of the marginal ice zone temperature, similar to the ice surface temperature retrievals. But there is a large component of variability in this region where we have mixed ocean and sea ice, of course.
Yeah, so difficult to get there and really validate.
Yes. So if anyone has good data for validation, we would appreciate that.
Thank you, then, Jakob. I think that's the last question. We have now walked through all the USAF CIS products. So thanks to all the presenters. And now we will open the floor to another session where we have invited 3 users to say a bit more about how they use USAF data. So I hand over to Olivier, who will moderate this session.
Yes, thank you, Steinar. Thank you all for your presentation from the OSISAF CIS parameters. I'm Olivier, and I recently joined the OSISAF team at Meteo France as Scientific Communication and Outreach Officer, and I'll be moderating the last session where some users of CIS products will share their application examples with us. So as Steinar just said, we have 3 invited presenters. We have Stefan Hendricks from Alfred Wegener Institute, which will show us an application about sea ice type. We have Johanna Caragalli from DMI. She has been briefly mentioned also by Jakob just before, because she will show an application about SST and IST products. And then Steinar, who has been moderating before, will present us a few slides shared kindly by Helen Beggs from the Bureau of Meteorology of the Australian government, showing us a few applications in the Southern Hemisphere. So we will start with the presentation from Stefan Hendricks. If you can share your slides. Yes, so Stefan works on remote sensing of sea ice thickness at the Alfred Wegener Institute about polar and ocean research. You're welcome to speak, Stefan.
All right, yeah, thanks. Can you hear me all right and see my screen in full screen mode?
Yes, it's fine.
Okay, good, thank you. Yeah, I'm going to talk about sea ice thickness, and I mean sea ice thickness is is a variable which is very, very tightly linked to all the different parameters we heard before here today in this webinar. And we specifically use the OSISAF CIS type product here for 2 applications. And I just give a brief summary of 2 of them. And I mean, this is work of a lot of people. I mean, specifically input here also has given this presentation by Robert Ricker, but there are also many different teams working on CI sickness in C3S by ESA, who are regular users of this data and providing input to the CI sickness algorithm chains. And I mean, one particular method we use is satellite radar altimetry, which in the end, we produce these monthly CI sickness maps. This is just here one example in April, where we actually have, because the radar altimeter just gives you data along these narrow tracks, we have to aggregate data from an entire month to get full Arctic coverage. And in essence, how this method works is that altimeters measures the freeboard, this is the height of the ice surface above the water level, and then converts into ice thickness. And we need 2 different inputs to that. And this is the mass of snow, basically just weighing the ice down, as well as the CS density. And both of these parameters, they are known to vary. They are very significant for getting CS thickness right. And both of them are not really observed on the same scales as we have radar altimeter data. So we have to use parameterizations for both data sets, and CIS type can be used as a proxy together with climatological information of snow depth and CS density. And I mean, the way this works is basically that we take the flags in the OSISAF CIS type data and interpret them as multi-ice fractions. So open ocean is open ocean, though there is no ice. And for first year ice, we say the multi-ice fraction is 0%. For multi-ice, it's 100%. And for the ambiguous type, we just interpret as 50% multi-ice fraction. And I mean, the difference between the 2 ice types is that first year ice generally has a higher density, because I mean, there are brine inclusions. There are also deformations, so like larger water inclusions. And generally thinner snow. So it is well known and well demonstrated that like the typical snow climatologies we have from like earlier Russian drifting station and aircraft landings, that nowadays it's no longer valid. It's too thick. So we use this first information to basically reduce the snow depth climatology. And for multi-ice, it's a bit different. So there we actually assume that the climatology of snow is still valid. But the ice of lower density, and this is because it's older ice, there are air bubbles in the ice, and that's what makes it lighter. And then we actually use the CS concentration data to do some gap filling here, because there are some data gaps close to the coast. And I mean, this actually is also significant here in the Canadian archipelago as the lower part of the screen, where we do have radar altimeter data that we're wanting to use. So this is then again how this then looks like just in the end. So we basically have the thickness of the snow layer. We extract the CS type information for the different tracks here. So what you see here is data for 1 week of altimeter data. So we merge the CS type with the snow climatology. And then for density of CS, it's basically a fixed value for multi-year ice and a fixed value for first year ice, and then scaled by the multi-year ice fraction. And then this then goes into the CS thickness retrieval. And then we can just compute CS thickness based on the assumption that we know the mass of snow and we know how much sea ice floats above the waterline. And then there's another application we use here, because what we also do is we then fuse sea ice thickness data sets from different sensors. And you see on the very left-hand side, it's the radar altimeter data. Again, just now sea ice thickness from Cryosat-2 just for 1 week. And then there is thin ice thickness from SMOS. So this is a completely different method, just estimates sea ice thickness from surface emissivity at L-band. And we want to merge these 2 data sets with an optimal interpolation scheme. But we also need a bit a kind of masking for when we merge the data, and how maybe also even mask individual data sets. So for example, because SMOS is depending on surface emissivity with a fairly low spatial resolution, there are often biases in multi-ice areas when there is in fact open water. So we're using here the sea ice type mask to then mask these out, because I mean there would else be a thickness bias, because I mean the ice there would be usually relatively thick, but then the SMOS algorithm, because of the open water set, might provide thin ice with a low uncertainty value. So this is not good for the optimal interpolation. Yeah, and then just quick summary. I mean, the products we use is obviously OSI 4.3 for near real-time applications. We use it at a latency of 48 hours. And then for the longer CI thickness climate data record, then we actually go not to the operational products, but then we use the CI's type climate data record as well. And currently we're looking here at data since ERS1 of 1993. I mean, it is a very, very important data set for us, simply because our processing chains fail if we don't get input. So there's obviously a high impact of data denial. And we found some issues. Sina has mentioned some caveats before. In addition, at some points, we see that actually heavily deformed first ice sometimes seems to also be classified as multi-ice. And we're looking at that in future updates. And as well, in the end, where we want to be in the future, I said we also want to get CS type information from the radar altimeter waveform data as well, at least in a data fusion way with the CS type, simply because there is small patches of first year ice in multi-ice areas, and with the altimeters, there's a higher chance of picking that out simply on the resolution of the sensors. And yeah, this is the application I wanted to present today.
Okay, thank you very much, Stefan, for this input on how you use CIS data from the OSI SAF. We will take all the questions to the users at the end of the 3 presentations. So if you have questions, please use the Slido and we will select from there at the end. So we will now welcome Joanna Caragalli from DMI to let us know more about how she uses SST and IST at DMI.
Hello from me, thank you. Just a question like everybody else. Can you see the slides in full
Yes,
mode?
everything is fine. We can hear you.
Perfect.
Slides.
Thank you. So my name is Joanna. I've recently joined the team at DMI. So I'm fairly new to some of the things presented here today. And I've been invited to give you a brief presentation on some of the user cases at DMI where we use OSI SAF ice surface temperature, but also sea ice concentration data. And with that, I would like to move on to the next slide and give you the overview or the general overview of how and why we use the data. So we are a production unit for the Copernicus Marine Environment Monitoring Service, and specifically the CI stack, for which we produce level 4 optimally interpolated products for the Arctic. And these are related to the sea and ice surface temperatures. And you can see some examples of how these data look on the data visualization tool of the Copernicus Marine Service on the right-hand side. And we typically produce 2 types of data sets. One of them is a daily optimally interpolated analysis at 0.05 degrees, and it's produced daily and delivered daily for the day before. But we are also responsible for producing at regular intervals, or updating and then delivering at regular intervals a reanalysis product which is homogenized along the years, expanding from 1982 to last year, to 2021. For these products at DMI, we ingest some OSI-SAF products, and these are typically the level 2 METOP AVHRR eye surface temperature product from 2015 onwards. We use some CIS concentration files, a near real time and an older type of data for classifying what is ice and what is not for our processing chain. And we are also using, or we have used in the past, the ASTI version 2 data, which is not a part of the OSI-SAF, but version 3 will be produced by the OSI-SAF, as we've heard before. So I'll give you a few examples of how we use this data. Here you can see a typical example of how we go from daily level 3 SST, IST products on the leftmost side, which are they are not gap free, so they have gaps, and we move through our processing chain. We move to a gap free level 4 daily SST, IST product on the second figure. And for that, to do that, we also use this surface mask to characterize what is ocean, what is marginal ice zone, and what is sea ice. And along with the level 4 product, we also estimate and produce level 4 uncertainties. This is part of a study that will be submitted soon by Nielsen, Enlist, and et al. It hasn't been submitted yet, but you can keep your eyes open for a publication later this year. Another example of how important this data is that it allows us to create level 4 long archives. I don't want to call them climate data records, but when we are able to produce these long archives of data from 92 onwards, we are able then to estimate monthly mean and yearly mean anomalies of the combined ice surface and sea surface temperatures for the Arctic and the associated trends. And this shows an example of how we can then, using OSI-SAF data, produce level 4 data that can be used for further research and monitoring of the Arctic. When it comes to the sea ice concentration data that we obtain from the OSI-SAF, we have actually investigated filtering criteria in the past. And what we are doing now is that we are using the unfiltered data, and there was a kind of presentation about that topic from Fabrizio in the beginning of the webinar, and we are implementing our own filters, especially to remove spurious ice, but also to improve coastal coverage. And one typical example of that is, for example, when we look at the OSI-SAF product, especially in the Baltic, there's information missing that for us is essential. And then when we post-process that product, we are able, for example, to cover the Baltic Sea in a more satisfactory way. And then just a kind of quick mention of the ASTI dataset. And I know it's not still an OSI-SAF product. It will be in the future, but an example of why is this relevant and how it can be used is one of the ESA CCI on land surface temperature user cases, which we've been part of at DMI, where we use the ASTI dataset. You can see an example here on the top left panel, along with temperature information from MODIS and AATSR, so different inputs to actually go to from data with gaps and to go to level 4 data, daily data that actually represent the ice surface temperature over the Greenland ice sheet. And one of the key messages here is that when we have actually been comparing the different sensors or different data sets within C2 data, we have seen that ASTI data is extremely stable and have a very good performance over different parts of the Greenland ice sheet. And this is part of a paper that has been submitted in the cryosphere. It's not, it's under review at the moment. So it's a valuable data set, and we would like to see that continued. And with that, I won't take more of your time. It was just a brief mention of what we do at DMI with OSI-SAF data, but to sum up, obviously we consider OSI-SAF data valuable. We identify an issue with the naming conventions for variables, and that's something that was mentioned before as well. We think it's very important to have a consistency in algorithms for the ISD products, both the near real time, but also the climate data records. And of course, as I've mentioned before, having ASTI version 3 available is a nice add-on. One of the main issues that has also been mentioned by previous presenters, Jakob being one of the last ones, I think, is that it's important for us also as level 4 producers to have a routine and consistent validation, and for that reference observations are very, very important. And
Okay.
with that, I would like to thank you.
Thank you very much, Joanna, for your input. We will have a few words from Steinar Eastwood about applications at the Bureau of Meteorology.
Yes, you see my slides now?
Yes.
Yes, so I'm here to just to present some work and input from the Australian Bureau of Meteorology. It's way past midnight in Australia, and they are also on holiday, so they couldn't join us, but I'll present their slides. It's interesting to hear what a Southern Hemisphere user is using our the OSI products for. So this is work done by Helen Beggs and her colleagues, and we'll see some requirements for CIS products for their different applications, and for some of the first results. So for CS concentration requirements to the systems at the Met Institute in Australia, for global coupled ocean models, ocean and CS models, they use they have now a demonstrator project to produce sea ice forecast services for the Antarctic shipping this year, and for that, level 2 products are preferable for data assimilation. For their SST products, so they produce SST products from satellites. They need sea ice concentration for masking of the sea ice, and for that they use a level 4 product from Ostia. And then finally, from their different SST analysis from NWP and other applications, they also require a gap-free level 4 CS concentration product, and for that they use Ostia. So I'll show some details on these 3 applications. So the level 2 CS concentration product is good for data assimilation, as it as the most frequently updated product with the least latency, and they are currently using the SMIS and AMSA2 level 2 products in their data assimilation. And for that, they grid the data, and they use the uncertainty in the uncertainty variable in the level 2 files as a weight in the gridding, which is good to know. But they also note that these uncertainties, they are tuning that way of weighting and the way of using the uncertainties as the uncertainty in the product is they might need higher uncertainties in the way they assimilate. Level 3 products is used more as a backup in their ocean models, because the main source for their use is the level 4 CS concentration product from Ostia, which actually used the OSI-SAF input in their analysis for producing the Ostia product. And the main reason for this is shown here in the last slides, where they have looked at the difference between an OSI-SAF level 3 and the level 4 from Ostia CS concentration product. And the main issue here is that the level 3 product has a more strict or conservative land sea mask, and this is because the satellite data cannot be used too close to land, because it will then be land contaminated and give false ice. So many users then need a level 4 product with gap filled ice concentration along the coast, and that they can do themselves, of course, or use the level 4 product like the Ostia product. So that was just a brief look at what they're doing at the Bureau of Meteorology in Australia.
Okay, thank you very much, Steinar, for browsing us through the presentation from Helen. So we are at the end now of the webinar. We had a few questions for Stefan Hendricks. I saw he already replied. It was about sea ice thickness in the southern hemisphere. I don't know if your microphone is open, Stefan.
Yeah, I can also just answer them. I mean, sea ice thickness in the southern hemisphere is not yet like operationally distributed. We are working on it. There are issues with, especially with radar altimetry with the snow layer, which is a bit less behaved than the northern hemisphere. So they're being worked on, but they will very likely have a lower accuracy than the northern hemisphere products when they are going to be released. But they will be released at some point.
Okay, thank you.
Yeah, and for the other question, whether the ice thickness plots are openly available, the answer is yes. I can only recommend, for example, for C3S, for the Copernicus climate data store. There's sea ice thickness, there's the MERS cryosats MOS product. This is distributed through ESA. And I just put 2 links in Slido to that question, where to get them.
Okay, thank you very much. We don't have more questions for the users, so I think we will close it here. But it was very interesting to see that you use the different levels of sea ice products from the OSI SAF, and especially that you get the data from different data sources that Steinar also presented at the beginning. So don't hesitate to go on the OSI SAF website, or you can find the data actually mirrored on other platforms. So I will now leave Steinar for a few final words before closing with Christine. Or maybe Christine steps in directly.
I can. Steinar, would you like to go first?
No, thank you. I just would like to say thank you to the presenters, and over to you, Christine.
Thanks very much, Steinar, and thanks very much also from my side to everybody who spoke today. That was really interesting. I also learned a lot, and I have even more questions that we may want to discuss offline. Thanks everybody for attending and for hanging out with us for the last couple of hours. We would really appreciate if you could give us your feedback on how you found this short course. This is really important for everybody who contributes to organizing and conducting these kind of short courses, what your thoughts are, what you think, what you may wish to have different, or what your suggestions are to improve these short courses. Maybe you even have ideas for topics for further short courses. So at the Slido, you will also find a section that is called Poll. And if you go there and if you could fill out these questions, that would be really, really helpful for us and much appreciated. I would also like to give you a bit of an outlook on what's coming in terms of short courses in the next few weeks and months. And obviously, as this was announced, there's a series of 3 short courses. The third short course of the OSI SAF is coming up next week. And we have touched the topic a couple of times these days. You heard the term climate data records quite a few times throughout this afternoon or throughout the last couple of hours. And some of you may wonder what this actually is, climate data records, what this means in comparison to near real-time data and maybe even interim climate data records. And next week, we will explain to you what this is, what this means, using the examples of OSI data. So for all of you who are working not only with near real-time data, but also with historic data, and especially if you're working over longer time scales, then I really, really strongly recommend to join in to this session, and I'm sure it will be interesting. There are also other short courses on different topics coming up. Maybe you realize we have regularly the data access drop-in sessions at EUMETSAT, where we explain and demonstrate the general data access of EUMETSAT, but also other topics you may be interested in. And also for our longer and in-depth short courses, please have a look at EUMETSAT.training.in for further courses, and of course also visit the OSI web pages for further information about the OSI data. And I'm sure the OSI team is happy to answer all your questions also via their help desk, and suggestions for what you need in order to make use of their work and their products in the future. So thanks very much for coming, and have a nice rest of your day, and hope to see you back next week.